Let's open the conference. Welcome everybody. We will open officially a little bit later, but that's no problem. We are very, very happy to have Professor Marta Kwiatkowska here with us. And it's really an honor and a great pleasure to introduce her today. So she's a professor of computing systems and a fellow of Trinity College at the University of Oxford. And Professor Kwiatkowska started her excellent career in Krakow in Poland, where she received her Bachelor and Master of Science degrees in Computer Science, summa cum laude, from the Jagiellonian University. She then moved to the UK, where she received her PhD in Computer Science from the University of Leicester. And in 1984, she became Professor of Computer Science at the University of Birmingham. And then in 2007, she became the first female professor in the Department of Computer Science at the University of Oxford, which is now heading the Automated Verification Research team. The main focus of Professor Kwiatkowska's extensive research career is on the development of modeling and automated verification techniques for computing systems. So with the increasing reliance of our society on computing systems, the development of such techniques are ever more important to guarantee a justified level of safety, security, reliability, and resource-efficient operation of such systems. So many of us probably know her from her extensive work on the development of the probabilistic model checker PRISM, for which she received the Ada Lovelace Medal from the British Computer Society in 2019. And PRISM is still widely used and an active subject of research by many research teams at the universities all over the world, as well as a great resource for teaching quantitative formal methods and model checking. Well, probabilistic model checking has been adopted in many fields, including distributed computing, wireless networks, security, robotics, healthcare, and many other areas. She's also the first female winner of the Royal Society Milner Award in 2018 for her outstanding work on stochastic and quantitative model checking. And in 2020, she became a fellow of the European Laboratory for Learning and Intelligence Systems. She's also winner of 2 European ERC grants, advanced grants, Veryware and Fun2Model. And furthermore, she is a member of the Responsible AI Working Group of the Global Partnership on Artificial Intelligence and the Digital Technology and the Planet Working Group of the Royal Society. So in this context, she is actively advocating a responsible adoption of trustworthy AI. And this brings us to the topic of her presentation of today, which is safety and robustness for deep learning with provable guarantees. So we're all very happy to have you here, and we are looking forward to your presentation. And to the audience, I would like to say, if you have questions during or after the presentations, just type them on the chat and we will address them during the discussion. So Marta, very much welcome. The floor, or maybe better, the screen is all yours.
Okay, thank you. Thank you for this very, very kind introduction. And thank you for the invitation. And most of all, thank you for your help with fixing the technical issues with this presentation. So I hope I can continue without any issues, but apologies in advance. We are living in a digital world, and this is why I can't be there with you. So what I'm going to talk about is not PRISM. It is related to the recent developments of AI, which is these days powered by machine learning, especially deep learning. And this is why I began to focus on this because of concerns about safety of such systems. But having said this, I will come towards the end, and with this work also I'm heading towards probabilistic model checking, and perhaps at some point also PRISM. So to start with, I think we are all, aware of the unstoppable rise of deep learning. it is something that's dominating not just the research, but also the news. But what many people don't realize is that the idea of neural networks which underpin deep learning is actually not that new. It goes back to 1940s, and the idea at the time was to develop a computing device that's somewhat similar to the way that neurons in the brain work. But the technology was not ready to implement these devices. So it took until 1998 when the first convolutional nets were proposed that focus on features, and they were actually used in vision. But then we needed to wait for GPUs to train these networks. And then from then on, things moved very fast through the vision breakthrough, win and go against a human. And of course, in 2019, there was the Turing Award given to the researchers who actually founded deep learning. So why now? Why not then? I think I've already said GPUs play a very important part, and they are now probably in your desktops. So many models can be trained just at desktops. That really facilitated a lot of experimental work. But of course, it is also because we have big data, all the Facebook images, labeled images that are easily accessible. Also, the models are relatively easy to build. I'll say more about this later. And inference itself has become much more powerful. So because of that, there is, of course, a lot of interest in deep learning in industry. It's being used for face recognition, it's being used for self-driving, and also in medicine, for clinical decision making. And the stakes are rising even higher. If you are on top of the news, Elon Musk's new initiative is actually trying to develop a brain-computer interface. Now, because of all this excitement of deployment, and there is a lot of excitement, not just about deployment, but also about development. Many students are keen to work on deep learning applications. But I come from the formal verification background. So when I first looked at deep learning models, I started questioning the way that these models are developed and then presented to the world for the applications. So the question that I'm asking really is, in all this, should we worry about safety? Now, if you consider something like a self-driving car, and this is an example which was run by my students' program, what it takes images. These are real urban images taken by the dashboard camera. So they are pixelized images. And there was a challenge to devise a neural network that would classify such images into those which have a traffic light, and then if they do, whether the traffic light is green or red. Now, what my student did, and I will explain how he did it later, is with this program, he's able to find sometimes just one pixel. It's enough to change one pixel. And then if you have an image with a red light, you change one pixel to green, and it changes the classification to a green light. So if you are sitting in the car and the car is attacked by something that knows about how my student's program works, then that car can actually start moving. And this is obviously a very unsafe situation. So back in 2017, I started asking the question, can we actually employ verification techniques to verify that these kinds of behaviors cannot occur? And of course, as well as my questions, I think there is a lot in the news about the potential dangers of releasing systems too early. In particular, both Tesla and Uber have already been associated with fatal crashes. Now, I mention them both because they use very different vision technologies. Tesla, in particular, it's all conventional cameras, whereas Uber uses LiDAR. So the images that I've shown you, they were taken, they are dashboard images taken by a conventional camera, but I will come to LiDAR images later. But of course, you know, the question that engineers who deploy this software, and also users, I mean, people do rely and love using Teslas, you know, they ask, but, you know, the system, when it comes, it says on the box that it has 99.9% accuracy. So how can such accidents happen? I will explain this as part of my talk. Now, what I should say right at the beginning is the machine learning community and the deep learning community, they already knew for some time from around 2013, 2014, that deep neural networks are not stable. And in fact, it is very easy to fool them. And this is a typical image that you may have seen. If you take an image of a panda and add to it some noise, so this is, the noise looks like this, but then it's multiplied by 0.007, so you're modifying each pixel in a very small and to a human imperceptible way, because the image looks still like a panda. However, the neural network, and these are the neural networks that are trained to beat human vision, it will classify it as a gibbon, or sometimes as something completely different. So these kinds of attacks, they could be practical attacks, potential security risks. They are sometimes artificial white noise, like this one, but they can also be deliberate, because they can be adversarial attacks. So you can imagine someone, an adversary, taking hold of the communication network of your car and then modifying these pictures. They've also been shown to be transferable between different architectures, and they don't just full image classification, but also the whole range of application scenarios. So software verification is something that I have been working on for about 20 years. And I started looking towards software verification for some answers. Now, what software verification does is it takes a program, a computer program, and develops its model. Now, this model can be developed post hoc or can be automatically generated. And this model usually looks like a transition system. And in this case, I'm showing you an example of a probabilistic transition system where transitions are taken probabilistically. There are also other kinds of models, generalizations that you need to consider if you want to represent quantities such as energy and time passage. In that case, you might want to add time in the form of clocks, and another model here is the timed automaton. And neural networks are actually a very different kind of models. So what modeling does is it employs rigorous mathematical abstraction where verification enables us to provide proofs that the model satisfies the specification. But more and more, we are now looking towards correct by construction synthesis of models from specification. You can think about it like optimization, finding the best model that fits the specification, because there will be a whole range of models. And the objective of model checking, which is an area that I'm active in, is to develop these proofs completely automatically without human involvement. But machine learning software, deep learning software, is actually very different from conventional software. And that is because it is developed using very obscure techniques, such as stochastic gradient descent, which optimizes the values of the weights. So it is considered a black box, something that is very difficult to interpret and explain. And the programming activity, when we write programs in something like Java, then we tend to use the logic if, then, else. But for programming using machine learning, this is much more pattern matching than using logic. You've seen that pattern. For that pattern, you need to match that action. Corner cases, we know about corner cases. These are some tricky combinations of decisions, but in machine learning, corner cases are actually unseen examples, like this image with a dashboard and a green pixel in it. That's an unseen example. It's not a missed condition. The data quality and data coverage is also crucial, and accuracy, this 99.9%, can be very misleading, as I will explain. Now, I started working on verification for neural networks in 2017, and since then a number of people have followed, and they are developing techniques, but it is a very challenging problem, despite the fact that neural network programs actually don't have loops as such. So a conventional feed-forward network is just a finite series of transformations. So it is a very challenging problem, but it is a very important challenge because of the potential for safety risks. But I should say, even in this case, we also need synthesis, not just verification. So what this talk is going to do is to give a brief overview of progress, the progress of my work since I started sort of in around 2016, 2017. And I will focus mainly on what we can do to verify the correctness of neural networks. And at the end, I will also hint, without providing much detail, but I will hint how you can actually employ it in the case of a probabilistic variant of neural networks called Bayesian neural networks. Okay, so I'll start with a deep feed-forward neural network. So what is a deep neural network? Well, what you need to think about is that it takes as input points from a vector space. Each point here is an image, and in fact, it's a three-dimensional image because the third dimension is the color in this case. And these points are passed through layers. Each layer has a finite number of neurons, and what each layer does is that it performs a linear, actually an affine transformation, followed by an activation function. So this layer-wise transfer proceeds through the network until at the end it comes up with a softmax output and decides by softmax what best matches the input point. Now the networks, the layers can have different structure and represent and can then focus on different parts of the image. For example, convolutional will identify features in the image. So this is just the idea, and formally to set the problem that I'm working on and I will focus on in this talk. What you need to think about that image, and the problem itself will involve n vector spaces. We have the input vector space, but we will also have the intermediate vector spaces in between the hidden layers. Now what we are focusing on here is, okay, let's think of image classification. Image classification is a capital F, is a function which will take an image, this 3D matrix, and will map it to a label which denotes what this image is: car, truck, etc. So this is the human perception ability. This is not an easy to specify function. So what neural networks try to do is the lowercase f here will try to approximate this capital F based on m training examples. And each training example will have an image which is paired up with a label. And this neural network, as I said before, will be arranged in layers. Each layer will take in a point and then perform an affine transformation multiplied by a matrix of weights plus a vector, and then apply an activation function. Now, these activation functions these days tend to be ReLU, which is just simply max of x and 0, but there are also other types of activation functions that can be used. ReLU tends to be the easiest in our case. So we simply have a successive application of such affine transformations and activation functions, and when you get to the end, I'm just going to say that f of x is simply the class, the label that's assigned to the image. Right, so what do we do? Well, we build the network, we have an architecture, and then what we need to do is we need to train it. Training involves running stochastic gradient descent to optimize the values of the weights. So in order to do model training, we select a subset of the data points. And here I'm showing you an example of a two-class problem. That you have the light blue crosses and the pink dots. They are two classes. The task itself has this decision boundary, the dotted line. But the model, of course, is not going to be perfect because you cannot guarantee that you will be able to provide all the examples. So it will learn a slightly different decision boundary. That's common. Everybody understands that in machine learning. So in order to actually check whether the trained network gives correct answers, what we also do is we test. So we use a held out data set, and these are the darker blue crosses here, and we test, and the accuracy is simply the proportion of tests that the network passes. 99.9% would just mean that 99.9% the network gave the correct answer. But this image also shows the dangers of this programming approach. So, and how easy it is actually to fool a network. If I start from a point and use something like gradient descent to move, or an optimization to move to the decision boundary, I'm very likely to find a weakness in the model. And that's an adversarial example, something that's misclassified. So here what you see is you see ways that you can find these adversarial examples by moving closer to the decision boundary or in between the points where there are some critical points that perhaps have been moved out. So this explains why accuracy can be misleading. Now, robustness is a topic that machine learning researchers have already been working on for some time. They tend to link it to the smoothness assumption. And that's because the inputs to the neural network are real numbers. And we tend to assume that they come from a continuous space. So even, real images are kind of thought of as living in the space of reals, even though they are pixelized, they are discretized. So in that context, because we have a continuous space, if you are fixed on a particular point, the smoothness assumption tells you that there will be a small region around that point which will classify the same. Because otherwise, I think, mathematically speaking, topologically speaking, these would be intractable problems to deal with. So point-wise robustness, which goes back to Szegedy, is actually saying, well, my network's not robust, is if in that region around the given point, there is a point y which classifies differently. Now, this is a local property. It's only for a particular point. But you can obtain a global property by, for example, weighting local robustness with respect to the distribution, the input distribution. You just compute the expectation. That is also known. It's a very active area of research, but I will explain in what way this is different from the work that I'm doing. Okay, so what I want to do is I actually want to take as the basis pointwise robustness. So I have a trained neural network. I fix an input point x, and there is some region around the x where I expect the network to have the same answer as f of x. And I'm going to use this as a criterion for safety. So imagine that there is some critical decision that you need to make, and that decision depends on the answer at that point. So say that decision is, stopping at the traffic light. So it's the, whether the traffic light is red or green is the critical issue here. And for smoothness, you want the whole region to classify the same. So there will be some kind of diameter of that region, which I assume the user would give me. And of course, to compute the diameter, I need to consider some norm. I'm working in vector spaces. I can have distances, norms more appropriately. And we tend to work with L2, but these are only proxies, L2 or L infinity. These are only proxies because they do not precisely model human perception. For human perception, we need similarity metrics, for example, Bregman divergence or Mahalanobis metrics, to actually model the similarity between the 2 points x and y. So notice that safety here is defined as invariance of classification. A classification does not change if I move my point around that region. But I can also compute, if tractable, I can also compute what I say the maximum safe radius. So this would be the largest region within that classification does not change. And what I'm really after is not just this maximal safe radius, but what I also want to be able to consider is a group, a family of manipulations. So it's operations on these points. Think of weather conditions, scratches, camera angles, etc. Such that if I apply this operation to the point x, I know that the label, the network output, should not change. So what am I doing with this? So this is to contrast it with the training versus testing. My verification here is an identification of these green regions. Each will be around a test point, the darker blue here, a test point. But I can now guarantee the network output invariance over that whole green region. With the testing approach, it's only point by point. I aim to guarantee in that whole green region, not just for that dark blue point. So that's the main difference. So in the very first paper, what we proposed is to actually discretize the region around a given point and search exhaustively for misclassifications. So in order to discretize, you have to make some assumptions to actually have, completeness for a method. But these assumptions, I think later they were Lipschitz assumptions, which I'll come back to that. They allow me to provide provable guarantees of the decision safety for the whole region. Now, in that particular approach, in the CAV paper, the provable guarantees were reduced to a counting problem, and the verification was propagated layer by layer. And the important difference was that if I cannot find an adversarial example, I can deduce, because it's a guarantee, I can deduce that the network is safe in that region. And this is in contrast to search-based methods for adversarial examples, for example, optimization-based methods, which search, but if they don't find it, you cannot guarantee that it's not there, because they rely on heuristics such as, okay, let's just optimize it to get close to the decision boundary. But scalability of that method remains an issue, and I will here focus on an approach that handles the scalability better. So what do we do about scalability? If I have an image, I have, an input image. In this case, it has 4,000 times 2,000 pixels, and we also have, the third dimension. If you try to naively search for this one position that, if you change, it would actually catastrophically change the classification of the network. That problem is intractable because we are dealing with high dimensional spaces. We also have nonlinearities. We have real images, etc. So the idea that we have applied is, can we apply a structure to this problem. And in fact, human vision, and that's kind of already captured in a convolutional network, focuses on features in this image. And before deep networks became fashionable, there were techniques that would process an image and identify features within that image. The method that I mentioned here is known as SIFT, Scale Invariant Feature Transform. It will just blur the image and try to identify a key point, its coordinates, how important it is and how large it is, its radius. So what we do is I have a trained neural network. That trained neural network takes in an image, say, of this traffic light. I process that same image that I feed into the network by SIFT. So I extract from it a list of features, and I use a mixture of Gaussian model representation to have an intermediate representation. Okay, so notice I do it outside the network, so I can use it also as an attack method. I have an intermediate representation that that works not in exactly the same way, but it works in a reasonably similar way to the way that convolutional networks pick out the features. But that allows me to reduce the dimensionality significantly, because my search tree is not pixel-based, it is now feature-based, and I can think about it in terms of pixels within each feature. Now, in addition, what I use is I impose Lipschitz continuity. So we know probably from school or university that Lipschitz continuity limits the rate of change of the output given the rate of change of the input. And it is well known that all the activation functions and layers of deep neural networks are actually Lipschitz. It is not that straightforward to estimate the Lipschitz constants, but it is known that they are Lipschitz. So that means that for each Lipschitz network, there is a diameter such that every image within that has to share the classification label. So we can use this fact to construct the grid based on the grid, adjusting the grid size according to the Lipschitz constant, okay, in such a way that I can simply search just the corners of the grid, and if I don't find anything, I can deduce by Lipschitzness that there are no adversarial examples there. So estimating the Lipschitz constant is complex, but there are better and better methods now, and this method does not actually require a precise Lipschitz constant. It can have an over-approximation. The cost would be in the size of the grid, because the grid will need to be finer for large Lipschitz constants. So what I now do is I set up a game-based search. Game-based, it is a two-player game. The first player, I mean, the objective of the game is to search for adversarial examples. Now, if you consider a pixelized image, okay, if you, my game will then unfold into a finite game tree where the first player will select a feature and then the second player will select a pixel within the feature, and the game will continue. But because the image is finite, okay, the game tree is also finite. And the reason this works well is because I use a mixture of Gaussian representation to guide the heuristic search of the tree, and I also rely on the Lipschitzness for the guarantees. So for to compute the maximum save radius, I set up two procedures. One is using Monte Carlo search tree algorithm to come up with an upper bound. Any adversarial example found will be an upper bound on the maximum save radius. But I also have a variant of A-star search to compute guarantees. This is the lower bound. And what do I do with this? So this is an example of a search tree which starts with the image of the digit 7, alpha, and the game tree unfolds downwards. So we have features lambda 1, lambda 2, etc., lambda 5, and then the pixels within it, and you see the corresponding images of modifications to the image of 7, where the last one, the one in the red, is adversarial, because it gives me a classification other than 7, even though to us humans it still looks like a bit messed up 7. And to show you how these guarantees work in practice, so this is a neural network that's trained on the MNIST data set, and this is the digit 4. So this is local robustness. I've provided the image of the digit 4, and what you see in the bottom 2 rows are safe, okay, manipulations that were established by A-star search. What you see at the top is adversarial manipulations, and you see the converging upper bound and the lower bound. I should draw your attention to the fact that the scales are different. So the gap between the lower and upper bound in this case is still high. Now this has since been also extended to videos. This is a much more complex architecture because a video is a series of frames where each frame is an image. And for that, they tend to work with the optical flow representations. So adversarial examples here involve actually manipulation of optical flow. But you can compute the guarantees in a very similar way. The networks themselves extract features from each frame, and then the networks, and to process the frames, they use an RNN recurrent network architecture. But in terms of the game, the game setup itself is architecture agnostic, so you can use the same game setup in order to compute the guarantees. Now, in this case, we found various distortions, but also were able to compute guarantees for VGG networks. And similarly for text classification, so you can train your network for text classification, and in this case this is a topic classification. Other types of applications are sentiment analysis, etc. And what in this case I can show you is that you can have attacks on such text classification methods where they would try to find a replacement of a word with a synonym, so that you don't change the meaning of the sentence, but the classification is different. So this is a very, again, an adversarial attack, but in the form of text. Now, there are also examples where there are no synonyms found. So we can show we can have some guarantees of safety. And in this particular example, we work with a very similar, we use a different tool, but we work with a very similar notion of the maximum safe radius. And we can show, for example, for which words substitution is safe and which words are not robust, because replacing them will actually change the classification. So these tools can be used either to provide guarantees, but also to extend the range of tests and feed that back into training and retraining. Right, I will just finish off by getting back to the autonomous driving, which was the motivating picture that I had at the beginning, except that the motivating picture that I had was more Tesla-like, because it used a conventional dashboard camera. In this particular case, the image that I'm showing you is a LiDAR image. And it was taken by my collaborators at the Oxford Robotics Institute. They are developing software to actually classify objects using LiDAR in real time, and they have a methodology for that. And what you see here is the classification. So in red, the red bounding boxes, the red shapes are cars. I think some of them are pedestrians, and I think there was also a bike. I can't remember which is which. But this is how I got started. Now, LiDAR is a technology that's used in particular by Uber. It stands for light detection and ranging. So it sends signals and then interprets these signals in space as 3D, either point clouds, finite point clouds, or 3D matrices, occupancy matrices, where there is a probability of whether there is an object in there or not. So the idea is to use LiDAR to build a 3D representation, which of course it's harder to do with conventional cameras, although computer vision has made significant progress in there, and people are also able to construct 3D approximations of 3D views using even conventional cameras. So for LiDAR, think about a 3D point cloud, but of course it is a technology that's not very reliable. Because you have a lot of uncertainties. There could be occlusion. Some of these objects, can hide some other objects. The sensors can be misoriented, and decision making has to be very, very fast. So what did we do? There was a paper that claimed that LiDAR was a reliable technology. And the basis for that claim was the following. They've taken trained LiDAR networks on kind of these types of images. Then this is an image, of a car. And what they did is they applied modifications at random. And they showed that the accuracy degrades, but it degrades gracefully as you manipulate the image. So that was they claim. But when my student saw the paper, he thought, well, but what if you actually attack these networks adversarially. Now, it is well known that point clouds are finite sets. It is well known that it is possible and very easy to actually compute a so-called critical subset. So it's a critical subset is a set of points such that you change one, you will change the classification of the network. And then once you've computed it, you can simply attack the critical set. And my student shown, this is what this red curve shows, that you can then very quickly degrade the robustness of the same network. So in this case, he was able to show that the accuracy of the network went from something like 90+% to 0%, because for every single test image, he was able to find, on average, 6.5% of occlusion, which is not much, to change the classification quite catastrophic. So that's the state of the affairs for LiDAR, but I'm beginning to now look at probabilistic guarantees. And this is because requiring that no adversarial examples exist is really too strict. This is a very, very strong condition. So what we really need is we need probabilistic guarantees, and these probabilistic guarantees should take into account the dependence on the training data, so the learning process. And for this, there is a variant of neural networks known as Bayesian neural networks, which actually account for noise and uncertainty. And in addition to an output computed in the same way as a neural network, they can also produce an uncertainty classification. Now, that uncertainty can be interpreted as a probability distribution, posterior distribution. Now, the posterior distribution is then used in the decision making. So we are in the decision, we are accounting for uncertainty, and that could be uncertainty that represents an image that the car has not seen before. Now, this process of computing posterior distribution is intractable. So we have a way to actually estimate it using a variant of statistical model checking. And what we do is we have a variant of safety, which is now probabilistic safety. And the idea is, before I was trying to prove that all these points here classify the same. Now I want to say that the probability that there exists an adversarial example here is very small, okay? Or that the probability that all these points classify the same is very close to 1. So it's 1 minus some very small delta. And you can, in this case, you can use statistical model checking to actually compute bounds. What we also need to do is to feed the distributions through the network. For this, we employ linear band, interval band propagation and linear band propagation, but apply it to the weight matrices, not just to the input. We have to do it for both the input and the weight matrices. And we use the technology in the context of an autonomous driving controller. This is a so-called pilot net. It came from the DAVE project from some years ago. It's been developed at NVIDIA, and the idea is to have a neural network controller that's trained on real images taken by a car driven by a human, where the the training data are pairs of an image and the human control output. You can train the network on these completely in an end-to-end way. And that's PilotNet. What we are working here with is actually a Bayesian variant of the PilotNet. And we can, within that Bayesian network, use the additional quantification of probability to actually estimate the safety of driving as you change the input conditions. So as you change the weather, so this is actually not trained on human-driven data, it is trained on data from the color simulator, but in the color simulator you can modify the weather conditions to, for example, represent snow, etc. So that is my conclusion. And what I was aiming to achieve through this talk is to convince you that deep learning needs to be more critically evaluated before being put into practice, because there are significant safety and security risks. And I've also overviewed some methods that have been developed in my group, which have been applied to sort of standard benchmarks like image classification, but also videos and Bayesian network autonomous driving controllers. And I've also hinted at kind of the future direction, focusing on verification for these probabilistic machine learning controllers. And I think in future, we still need to look for better ways to provide training, to combine machine learning with logic. We need some kind of neurosymbolic methods, because these days deep learning software is integrated within conventional software. Similarly to verification, scalability continues to be a problem, but what we want is we also want to be able to develop more complex properties and correct by construction synthesis. In this case, correct by construction synthesis means combining training with the computation of the guarantees. So that's it, and I just wanted to acknowledge my funders for this work. So thank you for your attention.
Okay, thank you very much, Marta, for this very interesting presentation. I think we have a little bit of time for questions. Can you hear me?
Yes.
Yes, okay. I've seen one question in the chat, so it's from Hossein Hoyat. For you, and I'm going to read it. It says, since your safety verification definition, one probabilistic version, is an exhaustive search, I assume it cannot be used within an online classifier. Is that right?
Yes, that is correct. The very first method cannot be, it has to be used offline. And of course, what that means is I can only do it for a trained network. And then if you find that the guarantees are not what you need, you have to retrain your network. Okay. So ideally, what you would like is you would like to have a method that offline combines the computation of guarantees with some retraining.
Okay. I had also a question myself. I don't see raised hands, and I see one more question from Hossein, but maybe I asked one myself as well. You mentioned a number of, say, accuracy percentages. So something like we should already be happy if we have 99.9% accuracy in machine learning applications at the moment. But as far as I remember, if you look at safety critical systems that we were developing, say, in the past before machine learning came, we were thinking about accuracies of 10 to the minus 6. Is this gap still there, or are we heading towards more accuracy at the moment with the approaches you just presented, or where are we more or less, and how far could we go with this?
No, I mean, that gap, yeah, that gap is there. I mean, you are absolutely right. I think for safety critical systems, we tend to ask for 4.9. So yes, it's, you know, it's 0.9999. But I think part of the issue with machine learning is that the dynamics of that research is to focus on performance. And performance means doing things fast, not necessarily with guarantees. So this reliability issue is exposed only during deployment. And I think there you see different, you know, approaches. For example, Waymo is very careful because they take safety seriously into account. But other automotive companies are not that careful. Yeah, so the short answer is yes, there is a big gap because the majority of research in machine learning is still focused on improving performance, so making the methods work faster rather than more accurately.
Okay, thank you. I see one more question by Fateme Kassemi. She says, if in our training we add some of the points in the guarantee region, can we have synthesis correct by construction somehow?
Yeah, so people have done that before. So early on, I think they used adversarial search methods to identify additional points that you had to add to the training data. But unfortunately, that can create a bias. So it can create a bias, and that is not necessarily a good approach. But I mean, this is related also to the way that you train. You need to train these networks. If you have unbalanced, you know, data sets, you can also have a particular bias.
Okay. There are many questions. I think we're not going to be able to ask all of them. I want to take a last one by Mira Mezzini. And she asks, assume I have a neural symbolic architecture in place. How do you expect this to affect safety verification?
Yes, that's right. That's a very good problem. So if you have a neural symbolic architecture, you would then need to develop a method that can handle both. Now, if you focus on something like ReLU networks, then for those you can use SMT techniques or MILP techniques to verify them. And we know that MILP or, you know, SMT can also be used to verify conventional logic-based specifications. So I think you need a method that will integrate, that can handle both types of components, and they need to be integrated in the same algorithm and tool.
Okay. Okay, thank you very much. I think we have to leave it here with the questions. I apologize that we cannot answer all of them because of the time, and well, I apologize also for the technical problems we had in the beginning, but we really enjoyed your presentation. And well, if there are more questions, I think we can always write emails and ask.
Yes, so I think that's right. Probably makes more sense. So yes, if you could send me an email, I think with those questions, because it's easier for me to answer by email rather than in the meeting chat. But thank you for your questions. They are great questions. I'm happy to answer, but I will do that by email.
Okay, that's very, very kind of you. Very nice. Okay, so give her a big applause for what we can do on the internet. I don't know, we maybe have some way to say that, but anyway, I'm sure I speak for all of you if I thank Marta once more for her very interesting presentation. So thank you for having been with us.
Okay, thank you.